Yeah, welcome to this semester's first workshop. We're going to talk about blockchain security. If you attended the crypto seminar last time, there's a lot of overlap between that one, just because some of the same tech is being used, especially public-private key stuff. And also, we didn't touch too deep into elliptic curves. We have a little bit more of that today, so we'll talk about that as well. So there's a few announcements. Actually, there's only one announcement. If you are looking at any CTFs coming up, there's DEM CTF, which is it is well established. It's pretty exciting stuff. So we might play that this weekend. It's actually already started, so maybe we should make an account for that as well. So the outline for today is going to be a little bit of crypto. So we're going to go over some crypto concepts, and then we're going to talk about some blockchain concepts, and then how to develop some smart contracts, which are like the programs that you can have on a blockchain, and then how to attack these smart contracts. Yeah, so that's the outline for today. So we're gonna have a break in the middle as well. So there's a few interesting crypto concepts. The first one that we're gonna talk about is obviously we have messages and keys. So these are the fundamental things that you're gonna have in crypto. You're gonna be sending the messages, and you're going to be working with those messages. You're going to be encoding them differently, and you're going to encode and decode those messages with a key, which is a collection of bytes that is kept. Usually keep them somewhere, maybe on your local disk or somewhere, and use that to encode and decode a message. And so there's a few types of crypto. There's symmetric crypto, which involves you having a key, and you use the same key to encrypt the message and decrypt the message. So that's symmetric crypto. We're not going to do too much symmetric crypto, but it exists in some ciphers like AES and Caesar cipher that we covered in the previous workshop as well. And then there's also asymmetric crypto. Hello. We can get the HDMI working, so we're just streaming it through Discord for now. It's kind of awkward. But yeah, so there's asymmetric crypto. Asymmetric crypto is using two different keys. One of the keys you're going to be using for encrypting your messages. So actually, there are two keys that are the inverses of each other. So the purpose of each doesn't really matter. It's just you have to keep one of them private. And the private key you're going to be using for specific things, like for your messages, if you're making a message and you want to encrypt it and send it to someone, you use your private key to encrypt, and then the public key is the inverse of that, so you can use the public key to decrypt whatever you encrypted with your private key, and vice versa. So this is an example if you want to encrypt something. So let's say that someone wants to send you a message. Let's say Alice wants to send Bob a message. So how we would do that is we have a public key, Bob's public key. It's probably published somewhere online. So Alice finds that, and Alice uses that to encrypt their message, and they would have the encrypted message that Bob would be able to decrypt on their side. So how that would work is that Bob has his private key and he decrypts it on his side. So yeah, we're not going to go too deep into the actual algorithms for this, because we already covered that. There's also hashing. So hashing is this process of taking a message and then producing a hash, which usually has a few key properties. One of them is that it's a fixed size. Hashing is not only for security. Sometimes you want to use it for making programs, maybe hash maps or something like that. So making it fixed size is a good property, and also it's not really possible to make it infinite size unless you're wrapping the hash function around something else. And also, it should be very difficult to reverse a hash function, or very computationally infeasible to reverse a hash function, because you have something like the avalanche effect, which one bit change in the message would cause about 50% of the bits in the hash output to change. So it's not predictable which change is causing the changes in hash output. So that's basically hashing. And we use hashes for digital signatures, and digital signatures are probably the most important crypto concept for blockchain, because it's how we use digital signatures to communicate all the time on the blockchain. So a signature is literally just an encrypted hash, right? You have a hash and you encrypt it with a key. So that's essentially all it is. and it's used to prove that you looked over this message, right? So you have this message and you looked over it previously. So you could, I mean, technically what you could do is you could just use public private key cryptography and encrypt something, and then someone knows that, well, because this is your private key that encrypted this, if I use your public key, then it's probably you. But that's also too expensive to do at scale, so we have digital signatures, which make things a little bit cheaper to actually prove that you saw a message. So how this works is that you have a public key, and the public key, people are going to use that to validate your signatures, and you use your private key to create the signatures. So that's kind of how it goes. There are a few algorithms, but we're going to talk about UofTCTF for today. So the process goes like you have your message, and then you hash it, and then you encrypt it with your private key, and you get a signature. So that's what a signature is, right? It's an encrypted hash. And what you do is you want to send your message and your signature, and you would send it to someone else, and then someone else can verify that your message and the signature is relevant to this message, right? You saw this message before. That's the basic idea of the signature. So you're sending both of them. So the verifier, now that they have the message and the signature, they're able to actually cryptographically prove that you saw it, because what they can do is they can take the message and they can hash it, so they have the hash, and they can take your signature and they can decrypt that signature with your public key, because the public and a private key are reversible operations. You get the hash, and so you can compare the two hashes, and if they're the same, then that means that this signature corresponds to your public key. This corresponds to you. So any questions so far about anything relating to this? We're going to go into some ECC stuff later on. Okay. Should be fine. Okay, I think we'll continue on then. So, there's one more thing. So for signatures, the message and the key are the inputs, but sometimes if you use the same message and the same key, you get the same signature, right? Because it's deterministic. So sometimes you want to add a little bit of variance between them. So you have something called a nonce, which is just a number added, and usually it's public. So it could be like a counter, like the first message you send has a nonce of 1, and then the second one has a nonce of 2, and so on and so forth. But the idea is you want to append the nonce before the message, so that when you hash it and you go for all the operations, you get a unique signature. So not all the same messages have the same signature. We'll talk about why this is important later on, because there's an attack called the signature reuse attack, which abuses the fact that signatures could be the same across different instances. Okay, so yeah, now we're going to talk about elliptic curves. So elliptic curves are actually they're very math heavy. You don't have to understand it too deeply. They are curves, which is like a collection of points defined by this equation. So it's just a collection of points, but it's defined by this equation: y squared equals x cubed plus ax plus b, where a and b are constants. So you can do a few things on elliptic curves. You can add 2 points, and the way you can do that is, the way that is done is you have your p and your q points, and you would find a tangent between the two, and then you would find where it lines up on the curve. So in this case, it intersects the curve at this point, and you reflect it to get the result of the addition. So that's how you add 2 points. Now, more importantly, if you add the same points, you go through pretty much the same process. You find a tangent line of the single point, so p plus p. You just find a tangent line of p, and then you find where it intersects with the curve, and then you reflect it as well. So you're adding the same points, and multiplication is just addition multiple times. There is a property, there's a hardness that makes reversing multiplication really hard, because you're not able to know just from a point and the number of times you multiply it, how many times you multiplied it originally. So that's the idea there. Hi guys. We're trying to get the screen set up, so so if you want to see what we're doing, it's on Discord. Okay. So that's how you add points, and the key thing is that it's very difficult to reverse the multiplication of points. So there are two key parameters that we use when doing crypto with curves. So obviously we share the curve itself. So we share A and B, which are like the parameters of the curve, but we also want to share something else, which is called the generator point. And a generator point is a point on a curve. It's just, you can pick any of these points, but it has to have the property where if you multiply it by itself, or if you multiply it, the number of times it can be added to itself before repeating in a cycle, so before returning to the original points, should be a prime number. So you can add it onto itself multiple times, but the max cycle should be a prime number, and it should be a very big prime number. So there's an algorithm to find the generator points, but it's a little bit convoluted. Just know that there's a way to find one generator point, and it should be public, it should be known. And I'm not sure if it's unique, but it's easy to find. So yeah, so there is a specific curve that everyone uses on the blockchain, the SEC CP 256K1 curve, and it's used in Bitcoin. So the curve is actually just y squared plus x cubed plus 7, and then the generator point is this giant point here, and then the cycle length is this super long cycle, and it's prime as well. So they found it has a lot of very nice properties. Okay, so we can use these curves to do a digital signature. We can create digital signatures from these curves. And how it works is that we have the generator, which is known, and the number of times the generator can repeat, so the cycle order. And then we have our private key, and we get our public key A, which is we multiply our private key by the generator, and then that would be our public key. And we have our message. So how it works, and this is a lot of stuff, you don't have to remember this. It's just see it once and then you don't have to look at it again, I guess. But you have your message, you hash it, and then you have a randomly generated K, which creates a point. And this point is going to be somewhere on a curve. So this point R is going to be somewhere on a curve. You take the X value of R, and then you compute the signature like this. And you would randomly generate a value of V as well, which is corresponding to the positive or negativeness of this point. So the points are, right, it has X and Y as the coordinates. And what you can do is you can, if you only have the X, you can also find a Y if you just run it on this curve, right? Like it's like a function kind of. So you don't need to store the Y somewhere. You can just store V, which indicates if it's on a positive or the negative. Because if you look at a curve, there are two Y values, two possible Y values. So we just need to encode if it's on the top half or the bottom half. So that's what V is. And then R is just the X value of that point that we have. And this point is what we use to verify. So when we're signing, we create our signature like this. And it's like this because we want to have a way to decode and verify with the private key mixed in somewhere. So the final signed message, you would have the message, you'd have your signature, you have your point here, and you have the V as well. And so to verify, so this is just kind of thinking of it on the curve. V is it's not the Y value, but it's like a polarity thing of which Y side it would be on. But this is the signature, it's free values, it's SR and V. And to be honest, that's all you need to know. You just need to know the parameters of the stuff, and then the actual implementation actually doesn't matter that much. The actual algorithm doesn't matter. But to verify, right, you would have your S, and you get the inverse of S, and then you would find the original point. You're able to recover the original points from these values that you were given, and then once you have the original point, you can compare if their X values are equal. And so that's how you would verify it. And you just need their public key and then their signature to verify. Okay. And then there's one more problem. This is also used in some attacks. It's called signature malleability. So the fact is that when you generate a signature, you have the value V, but V is actually not used at all in verification, right? We don't actually use V at all in verification. So you're able to generate two signatures that are both valid. And this can cause some problems later on if you don't actually enforce that a V value be put in place later on. Okay. And there's one more thing, which is a hashing function that you might see a lot. And this is just SHA-free. If you've looked into that, it's the precursor to SHA-free. But you don't have to know about the implementation. Just it takes an arbitrary length input and then it produces a 256-bit unique hash, essentially. And yeah, so that's all the crypto stuff we had to talk about. If any of you guys have any questions so far, feel free to name them in chat. Actually, it's not too bad.
Sure, I have a question.
Yeah.
So when you say that you can use any, you can flip V.
Yeah.
What exactly do you mean by flip?
So.
And if it's not used at all, why can't you just choose like a random? Oh, that's not on the code.
Yeah. So no. So V is okay. 27 and 28 are just they're just what Ethereum uses, but it's a polarity. So like a point has the X and Y, but you don't actually need to write down a Y value when you're sending a message. So you just need to send like a binary, like is it at the top half or at the bottom half? Because the curve has the curve is Y cubed and all of that. So you have two possible Y values that the curve can be, and you just want to encode which side it can be. And the thing is, you can have two V's, and they're both the same signature, right? You can have SR and then V, and you can have V as the other one. So V can be two values, 27 and 28. You can have it be either one of them. And the reason why is because the verification actually doesn't use V at all, because it doesn't care about V. It only cares about the X value of that point. So you can have two signatures that are verified the same way, but they have different things. So that could be bad because if you're using a signature as like single use, if you have two signatures, then you could probably redeem the same transaction two times, which could cause some problems. Did that answer the question? Yeah, it's just a unique quirk of the curve, but the curve has a lot of properties like the hardness of the curve that you can't reverse the multiplication. That's also baked into this. So I guess that's why they use it. Okay. So we'll go into blockchain technology, and there's a lot in blockchain technology, but here's like a high-level overview. Actually, there might be some misinformation here because I'm not a blockchain dev. I just found some time to organize this stuff, my previous notes. So there might be some misinformation, but from my understanding, how it works is that you have all of these disparate components that interact with each other. So there's like a concept graph. You don't have to remember this because we're going to go over all of this in the next few slides. But the basic idea is you have a blockchain that is shared between a bunch of nodes, and those nodes comprise a network. And the network is just what is able to store the blockchain. So the blockchain exists because you're not able to take one central authority down. It's shared between multiple nodes, so everyone has a blockchain. And the blockchain is like a massive file, so you might download like a 1 terabyte blockchain file, but that's it. You have the blockchain now, you can share it with anyone else. And these nodes would also be able to get feedback and update the blockchain by adding new blocks, which are added by miners. And the miners are creating these blocks from transactions, which are sent by users or wallets on the blockchain. And there's one more thing called a smart contract, which is a user, but if you send that user some data, then it can run functions for you. And you can trigger some things like if then conditions, like if I call you 3 times and send me 300 ether or something like that. And you can also define other things on top of smart contracts like tokens, which are tradable items that you can move around, and it's enforced by some deterministic logic. So there's a lot of moving parts here. We're gonna break them down one by one, but this is kind of how they all relate to each other. So the first thing is the currency. The currency is what started blockchain in the first place, is that it was meant to be used for currency. So you have Bitcoin and Ethereum and Solana, and they're all the most common ones that are deemed to be layer one. And then you can build stuff off of these coins and the blockchain technology off of them to make different things. But these are the basic cryptocurrency, the things that are going to be sent back and forth between the wallets. Now, cryptocurrency, what gives it its value is obviously you can buy things, but it also is finite or effectively finite. So the way that you can like make money to add coins to yourself is either someone gives it to you or you mine it. And the thing is, when you mine it, you create it. So if you have a currency that is infinitely creatable, it's not finite. But the way that they solve it is that the reward for when you mine it will halve over time. So um, eventually it approaches a finite value because it keeps on halving. Something series. So yeah, so Ethereum and Solana use different methods. I think it's the gas price increases. I'm not too sure, but this is how Bitcoin works: is that the value that you get would reduce half after X amount of transactions, like 4 billion transactions. I'm not too sure what the number is. And so this currency, it has units. We're going to talk about Ethereum mostly today. So Ethereum has the units. It has weight. It has Ether, which is the highest value that you can send, and weight is just the smallest unit. And then there's some units that we use specifically for things like gas and all that. Yeah. So the key idea, like probably one of the two key ideas, is wallets, which are the users of the blockchain, and transactions. So wallets are one of them, and I feel like I made a typo. I was looking over the slides. There might be something, but wallets are the accounts on a blockchain. So these are just addresses, and the address is, I think it's 20 bytes. So in hex it's 40 characters, but it's 20 bytes. And wallets are literally just the users that can have some money. So if you abstract the blockchain completely, you can think of it like a JSON file where it's like wallets and a number of Ethereum. It's like a JSON map of that. But there's some more stuff as well. We can talk about the world state later on. But wallets are like the users. They hold the value of the cryptocurrency. And they also have a public key and a private key. And these are the ways that it's able to send transactions. So how am I able to know that this person is the one that's sending the transaction? Well, we have to use a digital signature. And the way that we implement the digital signature is a public and private key. And the address is just a public key, but it's the last 20 bytes of the hash. Types of accounts. There are two types of accounts. There are accounts for users. And so the user would just have an address and then some balance, and also nonce that would increment depending on how many transactions. And then you also have a contract account. And a contract account is an account, but it can also store some code on it. So it's what allows you to write programs on a blockchain for your businesses or your charities or stuff like that. And it also has a pointer to some storage that is stored on every single node. So you have transactions, which are the second most important thing. And essentially what they are is they're movement of money and data. They used to be only money before we added smart contracts to make the blockchain actually programmable. So it used to only be money, but now you can also send data. And so you can send like 20 ETH from one address to another address, and you would have the transaction, you would sign it with your private key, and then you create a signature, and you'd have your data. And the data, you only really need data when you're talking to a contract account, because the contract account has like functions and code that you can call. So that's what the data would have. And so if you just want to send money to someone, you just have the value and then you make the data empty. But if you're calling like a function, then you would send a transaction to the contract account with the corresponding whatever the data that it expects, and it would run the function for you. So if you're curious on the structure of this, you have the nonce, you have the gas price, and you have the number of gas. So this gas is paid out to the miner later. The gas price is the unit per gas, so maybe like 1 ether or 1 gwei. And you have the address that you're sending it to and the address that the transaction came from. And you have the value, which is the number of ether that you're sending. And then you have the payload data, the raw data that you're sending to, in case you're sending it to contract accounts, you would have that. And then finally, you have your signature to make sure that this transaction is traced back to you, to your accounts, that you actually issued it. Okay, so here's the thing. Here's one of the optimizations that blockchain does is it has blocks. And what a block is just a list of 1,000-ish transactions. So you have transaction 1, transaction 2, so on and so forth, up to like 1,000 of them. And you have an identifier for the blocks, which is the hash. And a hash is very cool because the hash is created from all of the transactions. And it also has a pointer to the previous block because you want these transactions to happen in like an order. So you want your block to point to a previous block to say that this was after this bunch of transactions. So that's why it's called a blockchain, is that you have a bunch of blocks that are pointing to previous blocks for previous transactions that have happened later on. And also you have the world state, which is the final list of like the JSON file, the final list of like wallets to number of Ethereum, that sort of JSON thing. So as mentioned before, the block hash is just a collection, or it's derived from the hashes of each transaction. So how it works is that you have the hash of 2 transactions, you create like a intermediate hash, and then you take those intermediate hashes and you hash that. So you have an intermediate hash, and then you do it so on and so forth until you have the final hash of the entire list of transactions. So that's the block hash, and that's how you can identify, how you can actually talk about a block. That's the identifier pretty much. And as mentioned before, a blockchain is just a chain of blocks. So you have your block that points to the previous block, so on and so forth. You can download it. So the blockchain is just a collection of data. You can download it. You can host your own blockchain if you want. Ethereum mainnet is like 1 terabyte, so it's kind of big. Maybe buy like a cloud server actually. Actually, a lot of blockchain nodes are on like Google Cloud or like AWS, so it kind of defeats the purpose of the peer-to-peer thing, or like single point of failure and the blockchain is gone. But if at least someone has a copy of the blockchain, then I guess it's fine. So yeah, so the blockchain is just this. You can download it, and you want to be able to add things. We'll talk about adding new blocks to the blockchain, and that's done by miners. I'm not sure if that's the next slide. Oh no, it's not. But yeah, this was like the JSON file I was talking about, the global states. It's literally just like a mapping of your address to your balance. And then depending on if you're like a smart contract or something, you might have some extra data as well. Oh yeah. Okay, so a node is just something that has the blockchain, and it's able to receive info from the network. So the network is always constantly sending some info to the node, like, hey, a new block just arrived on our blockchain. Please add this to your own local state of the blockchain. Or like, a new transaction happened. Please record this down somewhere. So that's how a node communicates to the blockchain. And how it actually communicates is through something called an RPC. So if you've done like web dev before, you have APIs. There's also like RPCs, which are a different way to communicate. And a JSON file with your function and then the things in the data, and then you're able to query or like do things to talk to a node to tell it to updates itself, like a new transaction happens, or you can ask it things like, what is the balance of this account? So even if you don't have a node, like you're not running your own node, you can still communicate to a blockchain by sending a remote procedure call to someone else's node. And if they configure it, they can return you info about the blockchain, like the balances or like the transactions that have previously happened on a blockchain. Okay, it's not in this diagram. So what a node stores is it stores some cache somewhere. I'm not sure. Okay, it's probably not in here, but it would store some cache of the transactions somewhere in here. because the thing is, the things that are added to the blockchain, they're not transactions, but they're blocks. And blocks are collections of transactions. So it depends on what transactions are validated in the block. So you're not adding each transaction, you're adding the block. So you need to keep like a log of the transaction somewhere. But it's not in here. So like a node stores like the blockchain and like some JSON RPC endpoints to communicate with it. It also stores an EVM for it to, depending on if no, yeah, it would store some EVM. The EVM is like what actually executes the things on a smart contract. So like every node is the server technically. So all nodes are executing the code because there's no central server. It would store transactions somewhere. Okay, whatever. So yeah, so blockchain network is a peer-to-peer network of these nodes. You want these nodes to communicate with other nodes, right? How are you able to send data between each other? Like updating the blockchain, well, you need your peer to relay the information sent somewhere from some other guy that's initiating the transaction. So like, let's say you want to send a transaction to the blockchain, you would send an RPC request to the closest node. So like, you would send it to like the closest node or like some node on the internet. Like maybe let's say your friend is hosting a node, you would send it to their IP address at that RPC endpoint, and then they would send that request to all of the nodes beside it. And then those nodes would send all of that request to the nodes beside it, and so on and so forth. And it just propagates like that. And if you want a new node, you just want to join a network, you actually don't know anything about the blockchain, you can ask your peer for a copy of the blockchain and all the relevant stuff. So that's called bootstrapping. So yeah, so in order to make blocks, and this is how the blockchain grows, is that you're making blocks, you would have to take a collection of transactions from something called a mempool, and the mempool is like the list of transactions and then the gas payout. So like how valuable actually mining this transaction would be. It's like a list of all of those transactions. So the miners take that and then they get a challenge. And a challenge is either proof of stake, proof of work, or something like that. And then they would solve this challenge. And once they solve the challenge, they would add that solution to the block, and they would broadcast that solution and broadcast a block to the network. And the people on the network are able to verify that the solution is correct, and they would add it to their own blockchain as well. So that's how blocks are created. And yeah, they get it from the mempool as well. So the gas is going to be the amount of Ethereum that the miner would get as a result of this. How blockchain grows is you have you're waiting 15 minutes before updating the blockchain. And at the end of the 15 minutes, you find the chain of blocks that is the longest and you accept that. So you're waiting like 15 minutes, and then after that happens, look at all the blocks you received from like your peers and then try to arrange them together and see which chain is the longest. Because that chain is the longest, you can assume that the most amount of work has gone into that, so you can probably accept that one. Just wisdom of crowds and stuff like that. So what this does is that, okay, these slides are kind of out of order. There's something I want to talk about called the 51% attack. Yeah, so the 51% attack is this attack that abuses the fact that a blockchain grows for the longest chain. So let's say you have like a very weak blockchain that is like only like maybe 5 people are hosting. Like there's only 5 nodes. So there's not a lot of computing power there. So what you can do is you can have your guys mine a separate blockchain off of the network and not relay that to the network. So you can create a super long chain, and maybe you have like 10 nodes, so 10 miners, and you can mine this really fast. So you can outmine the people on the actual network and then have a super long chain, and then you can broadcast this. So you broadcast all of your blocks to the network, and then all of the nodes would get your super long node that you found. So how this works is that you need to have 51% or more of the computing power. So if you have more than 51% of the computing power, you're able to create more blocks than anyone else on the blockchain. And you're able to relay that, and then you just control the state of the blockchain like that. And now what that can do is that can allow you to do something called double spend, which if people are using the blockchain in real life for like buying pizzas and stuff like that, or like playing games and like getting things, changing things of blockchain and exchanging it for real world things, well, they rely that the blockchain is just going to be one state of things, right? They don't expect that the previous transactions that they posted are just going to be gone after some point. So let's say that you have some blockchain that's updated to have these blocks in this order, so block A, block B. But now you have someone else broadcasting this new blockchain, and it overwrites these previous blocks because this chain is now the longer one. So it overwrites the previous blocks. So these were published before. So the people that did the transactions, they gave you a piece already, so they can't go back on that. But you go back on your blockchain transfer because you added all of these fake blocks, and now none of these blocks include the original transaction of buying the pizza and whatever. So this is what allows you to double spend because technically your money is not gone anymore. So yeah, so that's an attack with the 51% attack. There are some network attacks. So one of the network attacks is if you have a bunch of fake identities, and they don't even have to be nodes. They can just be fake identities that you send an RPC request to, and then you can tell them, you can like drop pings, you can relay false transactions to these guys. You can slow down the network a lot because of the way that the peer-to-peer discovers its peers. It's going to discover a bit, and then if these peers are your fake peers, you can just relay a bunch of garbage data to just mislead a few nodes. But in this case, you have like a chain of nodes that actually talk to other legitimate nodes. There are certain cases where you have a node that is completely surrounded by evil actors, and this would cause them to be eclipsed. So all of the traffic that they receive is going to be fake. So you can cause a specific blockchain node to have a full state of the blockchain. And if it were a node that is everyone's using, like maybe google.com is hosting a node, and then you corner it like this, they would have a fake blockchain. And so like people that are requesting info about the blockchain would just get fake data. But usually like those main things, the main ways that you connect to the blockchain are like you connect to like several of these nodes. So you don't really have this. So yeah, so again, the idea of consensus is that you want to make it so that you're not able to publish a transaction for free. You want to have a little bit of a challenge. And so this challenge needs to be difficult to compute, but easy to verify. So that's the basic idea of a consensus, is that you need to be able to show someone that I spent a lot of computational power on this, and they should be able to verify immediately. So an example algorithm is proof of work. So proof of work, how it works, how Hashcash works, which is the original one in Bitcoin, is that the miners need to find a hash. So they need to hash some specific, they need to find an input to a hash that is smaller than a given value, that is smaller than, let's say, 10,000. So they need to find that hash, and like you can't reverse a hash, so you have to try every single input repeatedly, on and on until it's smaller than a given threshold. So this is the hash cache. So that's an example of the proof of work, and you have a nonce as well, and a nonce would make it so that it is different every single time, because the hash is going to be the same for your input, but the nonce, when you add that to it, it's going to be different as well. There's also a different one called proof of stake. Proof of work has gotten a lot of flack because it's expensive, and you have people that are consuming so much water by doing it. So you have proof of stake, which is a little bit better. So how it works is that each miner would bargain some Ethereum, and it's I think so. There are like several different types of proof of stake. The basic idea is that you have to stake a little bit of money in a transaction, and that affects how difficult
the challenge is. So you have to stake a little bit of your own money, and the more money you give, the easier the challenge becomes. So how this works is that there's a revised version of proof of work, and it would just multiply the target by the stake, and then you just have to, you have like a bigger target essentially. So you have more things that are valid solutions. So that's an example of a chain-based proof of stake. There is, I think there's a problem. I spent a little bit of time trying to understand this. It's not really an attack that can work in the real world on like big blockchain networks, but it is a possible issue with proof of stake, which is that in proof of work, when a miner chooses to work on something, they would have to devote most of their time on that. But in proof of stake, you can choose to try to compute every single block because it's a lot cheaper. It's now a lot cheaper to make every single block. So a miner actually doesn't care which collection of transactions that they're minting, so they'd be trying to mint every single block. And the problem with that is that now you know the distribution of how many miners are working on each block. So if you dedicate a good portion of your own miners towards a specific block, you get a kind of a skew of the percent of the computation done on each block. So like maybe you have 99% of the miners on a blockchain minting one block, but then you add your own miners that are only trying to mint the specific block that you want to be minted. And so now there's more likelihood that this one gets minted because there's more computing power. But in like large networks, this is very negligible, right? Because you're going to have like a couple thousand miners, and if you need your own miners to actually make a difference, because it's like a very small difference, like 1%, you would have to invest a lot more compute power. But that's the basic the idea of this attack, which you can choose to control which blocks you want to mine with a little bit of higher probability, but it's kind of infeasible in the real world. There's a different type of proof of stake algorithm called nominated proof of stake, and how it works is that you have kind of like a roulette wheel. So you have each miner, and then they take turns. So a random function would choose which miner is responsible for the proof of stake calculations, and then they are the target. So no other miner can actually make the block. It's only one miner can make this block, and then they are responsible for giving the outputs. And it uses something called a verifiable random function. It's deterministic function that is shared between everyone, and then the private key would be able to include the private keys of all of these guys. So yeah, it has a proof, and you can verify that this randomness came from the private keys. And yeah, so there are also different types of networks. Like as mentioned, a network is just a collection of nodes. So you can have the same blockchain tech, but you can have different networks for it. So we have main nets, which are like the main network that you have your actual transactions on, your code on. But then sometimes you want to test things before you deploy it to the main net. So that's called a test net. And these are like examples of test nets. There's also some more test nets, but they're not. It's like the established ones have a lot more nodes on them, and actually a lot more miners, which is the important part. So for development, in order to get like Ethereum and all that, you can go to like an exchange like Coinbase or something to get some money, but that costs real world money. You don't want to do that. So for development, you go on a test net, and then you get some Ethereum from faucets. Now, the reason why it's called a test net, I don't know if I mentioned this, is that there's no scarcity. So we talked about the scarcity in that the gas rewards would reduce, but in a test net, you don't have that. So in a test net, you have infinite amount of coins, so then there's no actual value. So you don't actually care. So the people that are giving the free Ethereum, they're fine to do it. They just have to do a little bit of computation to give it to you, but that's fine. They give you like a tiny small amount because they still have to run their servers. Okay, so we'll talk about smart contracts, which are kind of the main point of today. When you're doing blockchain security, you're auditing the code of smart contracts. So smart contracts run on something called the EVM, which if you guys have taken a look at compilers and interpreters before, actually I'll take a look to see if there's any questions online. Okay, I don't think so. Looks fine. Okay, so yeah, if you've looked into interpreters before, essentially a virtual machine is just you have some instructions, like maybe Java virtual machine, you have like different instructions in Java code. If you ever compile Java, you get like a Java code, and you can you have to run Java, whatever my Java code is. It's not executable code, like you can't directly execute it. You need to use Java to run that. So that's what bytecode is. So Ethereum has the same thing as bytecode, and you have an interpreter that is reading each of these and it's executing it on your local machine. So like if you're running macOS, which has different processor than like the traditional ones that you can buy for like an x86 computer from on Windows and stuff like that. There are different ways that you run things on different computers, but a virtual machine is able to have a bunch of targets, like a target for macOS, a target for Linux, a target for Windows, and different processors, and it just executes it for you. So that's the basic idea. And how it works is you have a bunch of opcodes. So it's essentially like assembly. If you've looked into assembly, opcodes are very low level operations, and it takes its arguments from a stack. So if you've played around with like x86 or ARM or anything like that, they use registers. That's one way to have data, but you can also use stacks. And the way that works is you take some things from the stack and then you would pop some new values onto the stack. So we'll go for an example of this later on. The EVM has some things that is a program counter, which is like the counter for the current instruction being ran, and then you have the stack and a heap for some memory. But yeah, essentially the architecture is you have your instructions, and then you have a stack, and then you have something called account storage, which is shared between all of your peers. So the EVM has some things that are temporary storage, like you don't actually care about the value in it because it's just going to be replaced. So essentially it's private because it's just going to be replaced like almost immediately with different data. And also you don't care about the data. So you have the stack and you have the heap. The heap is technically not like the heap on other operating systems where you have like bins and stuff. It's just a large array of memory. It's like an array of memory. So it's not like a traditional heap, but it is essentially used similarly. But you have account storage, and account storage shares some data that is public. And this is important because sometimes you have code, you have smart contracts that write things to account storage, and it's meant to be public data, but they put it in the account storage and you can actually read that. So some challenges might have that. But yeah, so we'll go over an example on how EVM is executed. So let's say that we have these instructions here. We have push, two pushes, and then a multiply, and then a push, and then we're going to store some value into memory. We're going to push something onto the stack, and then we're going to load. So we'll run through each of these. So first we push a value onto the stack. This is what this instruction does. We push a different another value onto the stack, which is 0x2, and we multiply them. And what multiply does is it takes the first two values and then it pops them, and then it returns the multiplied value onto the stack. This is not 14. This should be 0xb, 0xd. I did the math wrong. It's not 0x14. Push, so you just push something to the stack, and then you would store. So mstore would take two arguments, right? It takes the address and it takes 0x14. And this stuff, if you're curious on what each opcode does, there's like a site, EVM opcodes, that is like a documentation for what each opcode does. But I'm gonna just move past this pretty fast. So yeah, so each of these opcodes do something. So you would store it into memory, and you saw it was added to the heap. The value 0x60 is the value 0x14. You would push a value, and then you would load. So what this does, what load does, is it loads the value at the top of the stack into the stack. So it just takes that 0x60, it moves 0x14, which is that value, loads it into the stack. And you can push something here, and then what balance does, balance would look into account storage and then return the balance. So you have different storages. You have the stack, which is kind of used as the arguments, and then you have the heap, which is larger things. Usually you use the heap for like structs or like large data structures or some things that you just don't want on a stack, and then the balance is the thing that is shared between all smart contracts. So yeah, now we actually talk about smart contracts. These are accounts, right? They're contract accounts, right? You have user accounts and you have contract accounts. So these are contract accounts that are responsible for taking the transactions that you attach data with, and then they run some code. So they're deterministic, and they're also immutable. So once you deploy a smart contract, you can't change the code. If you want to update the smart contract, you have to either tell all the users to use a different contract, or you can use like you can connect it to like Web2 and have like a URL of this, and then that URL reroutes the actual address. So you can have like a proxy for that address that you want. So yeah, so that's kind of what a smart contract is, and it has EVM opcode, so it's able to run some EVM functions. So a smart contract has code, and it just has EVM bytecode. And the way it works is that you have the structure of the code looks like this. You have a dispatcher, which is a few instructions at the top. They're essentially jump statements. If you've worked with assembly, you just jump statements. Depending on the thing that you give it, like the data that you give it, it jumps to function A. So like maybe it checks if the input includes like pay or like deposit, like a function called deposit. And then if it is equal, then you jump to function A, which is the function deposit. If it's not, then you just do something else. The actual way it implements this at the lower level is called a function selector, and a function selector is like a hash of the function signature, but you don't have to remember that. You have something called the ABI, which is the documentation for how this binary works. Because it's bytecode, you're not going to be able to read the bytecode, but you also kind of want to understand what functions it has. So you have an ABI, which tells you the addresses of the functions, the function selector for you to jump to, and stuff like that, the expected parameters, and some more things like the return type and all that. So Solidity is a way for you to write this EVM code without actually having to write the opcode, because you don't want to write the actual opcode, assembly code, whatever. You want to have like a high-level language that actually compiles down into it for you. So that's what Solidity is. And there's a few things. So it's kind of like Java, if you've written Java before, because it's object-oriented. So it's kind of similar. So there are a few data types. There's an integer, there's a mapping that is commonly used. So these are all the most commonly used ones. There's ints, there's a mapping, which is like a dictionary or like a JSON. There's addresses, which represent a blockchain address. And those are probably the main ones. And there's strings and booleans. Oh, and also there's bytes, but yeah, bytes is also used. So there's some context, and the context is stored in the account storage. If we go back a few, or like a ton of slides, we talked about, okay, this is actually a lot of slides back. But remember that the EVM has the heap, the stack, and then also account storage. So, okay, I'm just gonna close that. But it has account storage, and this is the storage that's shared. So you can actually access those in Solidity. And some of those things would be like the transaction number, the block number, and stuff like that. I'll just try to go back to the in that function, you like kind of dissect the transaction. That's kind of like your input data. So you'd be doing that. So yeah, so how a function works, actually, I might just skip this because it's not that important. There is something kind of important, which is a function can be payable or not payable. And depending on if it's payable or not, you're able to give it ether or not give it ether. And also a function can do things like you can specify that it only views the state, can't modify it. And if it only views, it doesn't actually cost any money to send a transaction to it. But if it does modify something, then you do have to give a little bit of Ethereum to the call. So in your transaction, you have to add like a tiny bit of Ethereum to the call in order for it to actually modify itself, because it's not going to do that for free. So something else very important is that functions can fail, right? They can error out. But the way that Solidity works is that if a function fails, then the transaction is just reverted. So no money is actually transferred. It just doesn't add it to itself. So yeah, it doesn't add it to itself. And you can trigger these errors by things like require statements or like assert statements if you've worked with that before. Essentially, it says that this condition, this Boolean condition, must always be true. If it's not true, then just signal an error. Go to the error handler. So that's a way to enforce something. It's like very commonly. Something also very important is calls. So a call essentially is the ability for a smart contract to call a different address. So you're able to send a smart contract a transaction. A smart contract is also able to send other people transactions. How you would trigger it is you would trigger by transaction, and then somewhere in the code it would send this call. So the smart contract can send a transaction to somewhere else. Because yeah, smart contracts only run code if you tell it to. So you would have to tell it to do this. But this is kind of how it is in Solidity, and you can specify how much money you give and then also the data. If you were to call somebody like an end user, so you're not on a contract account, you just call this, then they would return true. And this is important for something later on, which is when we're doing calls, sometimes we're just calling people to send them money, because you can just send money in a transaction. So sometimes we just send them money and that'd be enough. So success would always be true. But sometimes you can call other smart contracts, and then they have something.
Yeah, so I'll just explain call, and then there's also a different type of call called delegate call. So call just calls something else, sends a transaction to them, and it uses the smart contract's storage and context. So whatever the smart contract account knows, it uses that. So if you send some money to someone else, it would take the money that's stored in the smart contract address and it would send that money to someone else. And yeah, now there's something called delegate call, and delegate call is able to take the context of another transaction, so all of their functions, but it's calling it with our transaction's context. So if you have like a different smart contract with something like get update storage or something, or like maybe this is a library and this is doing something like SHA-256 and it's a library for that. Maybe you're delegating a call, so you want that function. You don't have that function, but you want that function. So you call them, and then they would give you the corresponding code, like the EVM code for you to run, and then you run that. And so you can think of some problems with that. Is maybe you have like a malicious other smart contract that has some common function name, and then you just you make it so that send all data to attacker account or something like that, and that could cause some problems. So that's also an attack that we can talk about later. Contract compilation process, it just creates API and stuff like that. And then the one thing that is also kind of niche is that if you want to deploy smart contracts, all you have to do is you have to send your transaction to the address 0x0. There's nothing at 0x0, but it's like convention. It's just convention, 0x0. Tokens we're going to skip. Tokens are not that important. And yeah, oracles we can skip. Oracles are a way to connect data outside the blockchain. So if you want a random number generator, you can't generate a random number on the blockchain because everything is deterministic. Everything has to be shared and everyone else has to get the same random number. So if you want a random number, it's going to have to be deterministic. You can't get true random numbers. Like you can't use lava lamps or anything like that to get true randomness. So that it's not a good idea. You have to use an oracle, which is like
something off-chain that is providing that randomness. And you also have anonymity. So if you want to send a transaction, but you don't want people to know that you're sending a transaction, so maybe this is for some darknet stuff, then you can send some money to a mixer, and then the mixer would forward that money to the other transaction. So you kind of have to trust the mixer, like whoever has the address of the mixer to not actually pocket your money, but usually it's fine because you're trusted. And for development, there are a few tools that you can use. I don't think we're going to build anything today, actually, but we can talk about it. So obviously, running your own node is expensive. You have to download the entire blockchain, and you also have to keep it up all the time, or else you lose some transactions. So you're able to emulate a blockchain for development purposes. So this is just emulated. It runs the EVM, emulates that, and it emulates the transactions and all that. So that's what Anvil does. You're also able to deploy. So you're able to, if you have like a smart contract on your file, you wrote it up and you want to deploy it to a network, you're able to specify the smart contracts file path. You have to have your address, so your address and then your private key, so that you can actually send this transaction, and RPC URL, which is the node that you want to send this to, and then that node would just publish it to the nodes beside it, and eventually it propagates throughout the entire blockchain network. Cast is if you want to send specific transactions. So let's say you just want to send a transaction, you can send it to like an address and a function, and you can send it some arguments. So this is for a smart contract. You can also send it to just regular user accounts. You just don't include the function name. You just make the function 0, like the signature, just quote, empty quotes with nothing inside. And yeah. You can emulate functions. So this would run it on your own EVM, so it actually doesn't send a transaction, but you can see kind of like a stack trace of what would happen if you called it. You're able to view the balance of accounts, and you're also able to read account storage. So remember that storage is shared. Sometimes people have public data on there. You can just read that with cast storage on that. Maybe I can try to explain what this smart contract does. So this is kind of a solarized theme, so it might be hard to see, but essentially what it does is you have a few functions, and all smart contracts also have a constructor, but it's not defined here. The constructor just sets up, actually you can define it, but by default it does nothing. So deposit, it takes your amount, which is a parameter, and it also is able to take the context. So the transaction context, whoever sent the message, which is message.sender. And so what it's doing is it's requiring that the money that you give it is greater than 0, and the message that the Ethereum that you sent in the transaction is the same as the parameter that you gave. And if it is, then it updates this local dictionary or like mapping, hash map of your address, message.sender, to that amount. And withdraw will do the same thing in opposite order. So it requires that you have your withdraw amount smaller than your account balance that is stored in this map. And if it is, then it's going to subtract a little bit from that, and it's going to send you that value. So message.call, so call would just send that value. That's how you send money. Because we're assuming this is like a EOA, like a user account, we just do this. We don't have to give it like a function name or anything. We just do empty quotation marks. And if it's equal to 0, then we can just delete this key. And if you delete a key in a dictionary, it just sets that key equal to 0, the value of 0. And required success is just if this did fail, if the transaction failed, then revert the transaction. So don't even do this. And check balance is a viewable function, so it costs nothing. So you can just call it, send 0 ether, and it calls for free because it doesn't modify anything. And it requires that it's not equal to 0, and it just returns the balance of that user. So that's what that smart contract does. Most of these you can just kind of pick up on your own what they kind of do. Off-chain transactions, we can skip this. Essentially, the idea behind an off-chain transaction is you want some data to be done offline. So you don't actually want to do a lot of things on the blockchain because it's expensive to publish a transaction. So sometimes you want to do things off the chain. And in order to actually have that verified by the blockchain that we can add this transaction to, it doesn't add it to the blockchain, but adds it to like the smart contract storage, is you have to have the other person's signature that this happens. So let's say like Alice wants a token from Bob, and they negotiate offline, like they negotiate in real life or something, and they agree. So Alice has like the message of the transaction of like maybe it has like token Bob to Alice, something like that, some more like actual message data that the smart contract would accept, and then Bob gives a signature. So Bob has a stamp of approval on it, and so Alice would just send this message and then the signature to the smart contract, and the smart contract would evaluate it by itself. Okay, so we'll go over a few attacks because we don't have that much time left. So probably the most important attack is called a reentrancy attack. So there's something, okay, yeah. So there's something that happens when you call someone else, is that remember that you can call and you can send some value, but you can also call a function. So usually we make this nothing because we want to send it to actual users. But what if we have, what if we call another smart contract and we define a function that is this? Well, then it would call that function, and when it calls that function, this function would cause, so in this case, this default callback function would continue to call this withdraw. So so this calls withdraw, and then from this context, it sends a transaction here. So it continues to call back and forth, back and forth, back and forth until the balance is more than the amount. So essentially what we're doing here is this is a bank, or this is a vault that has a collection of money, and it has it enforced by like a hash map. And then this attacker contract sets a default callback function to continue sending transactions. And because it's not returned, you end up like generating a few stack frames. So this doesn't go to the next line because it's not returned anything yet. It has to continue on and on and on. So essentially what this does is it drains the entire wallet of this contract. So that is a reentrancy attack. And the reason why this happens is because you are setting up your code to not actually do this interaction down here. So there's something called, we're going to skip this. There's something called check effect interaction, which is a program pattern. So you have your check here, then you have your effect, and then you have your interaction. So you want to interact with the other contract at the very end, because when you change your internal state, you want to change that before. So when you interact with it, you're not using the state from the previous call, right? So in this previous example, we actually called it and we interacted before we updated our state. So this is what's causing it, is that the internal state is not being changed beforehand. There is an attack that was very common in previous Solidity versions less than 0.8, which is arithmetic overflow underflow. So if you were able to give a very large value, which is not that hard to do, you have a very large value, and then it would wrap around back to a very small value. And if you have a very small value, negative value, it would wrap around to a super high value. So this can cause some problems as well. You have a delegate call attack, which is, as mentioned before, it would be able to call anybody else's code. So let's say you have this code that is that causes us in our own context to call this pwn function. You can call a pwn function. Actually, there's a better example with here, which is executes. There's a function called self-destruct, and what self-destruct does is it takes this contract and it forces this contract to send all of its balance to different contracts. So if you're able to make someone else delegate call, and then your function does self-destruct, you're able to blow up this contract and move all of that data to all of that Ethereum to some other wallet. So that's a problem. And also, these challenges, if you want to do them later, because we don't have time today, they're at these links. You can try them out if you want. There's another attack, which is accessing private data. If you want to access private data, you can use, what is it called? Cast. You can use Cast, that tool. And this stuff is in account storage, right? These globals by default are going to be in account storage. So if you have something like password, and then you set that password value, well, you can just access it because that account storage is shared. It's public. You can just read it. And yeah, the way that account storage is set up, this is very. You might do it sometimes. They have slots of 32 bytes. They're just 32 bytes storage slots. So if you read storage slot 0, it reads 32 bytes. Storage slot 1, it reads the 32 bytes at slot 1, which is for 33rd byte to 64th byte, and so on and so forth. So that's the way that it's organized. We'll move on. Here's another attack, which is a logic bug. So some smart contracts have a logic bug where they're looking at the smart contracts balance, so the contract accounts balance, and are using that for logic. And you can do things like you can send it some money from self-destruct. So you can define your own contract and then blow that up and then give ether to your target contract. And if they were like doing things, they were doing logic on that, their own balance, then you could mess that up as well. So there's another attack called front running, and this is like a man-in-the-middle attack that exploits the time between transaction and block creation. So transactions are added only when a block is created, right? And the block is created by the miner. There's going to be a little bit of time between that. If you are, I don't know, maybe you're in a better area, like maybe you're in the center of the world and you see someone else's transaction, you copy the same transaction and you can copy the secret. Like maybe let's say you have a smart contract that would return you, like give you some money by guessing a secret. And maybe the secret has gone from like an oracle. You don't want to store it in the account storage. Maybe you get it from like an oracle or something like that. So you have the secret and a victim finds a secret, right? They send it over. The attacker sees it and they send it the same. And then the attacker is validated first. So their thing is put in a block first. And then they get the money, but the victim sent it first. So they essentially stole the victim's things because they were in a better area and their transaction got validated first. So there is a way to prevent this, and it's called commit and reveal. And essentially what this is that you split up the part of communication. So you say that I have the answer, but you don't reveal the answer. And then at the very end, you say, once they acknowledge you, then you reveal the answer. So you have the time and then the actual revealing the answer at separate times. Yeah. So here's signature replay. So we talked a little bit, we didn't go too deep into off-chain transactions, but off-chain transactions, essentially you have a signature that someone else gives you, and then the smart contract would validate that. The issue is if the signature is reused over and over and over again, well, and it's not actually, it doesn't actually check how many times the signature is used. You can use the same signature for the same thing, on and on and on. And so like, what if Bob gives Alice permission to take one token, but then Alice takes several tokens with the same signature? So that's an attack. I wanted to set up a contract for that, but I didn't have time at the end. But also signature malleability. So the thing with the elliptic curve and the fact that you have two different values of V to have the same signature, if you don't actually properly validate that, that can also cause signature reuse attack, signature replay attack. So yeah, so even though we have signature replay protection, where it checks that this signature was executed before, we can just change V and it's essentially the same one. Okay, so yeah, okay. That is pretty much all the attacks we had. There was going to be some stuff on zero knowledge, but I didn't have time to finish it. So maybe we'll talk about that some other time.